In the last lessons, we learned how to draw Lewis dot structures. We also learned how to determine if a molecule is polar or nonpolar. And so the last thing that we need to learn about these molecules is their geometries, the shapes that they assume. Now, we looked at this already a little bit when we talked about the Vesper model, but now we're going to put names to those shapes. So I'm just going to go through and use this simulation to show you all of these different shapes, identify them, and then we'll do some practice with it. Okay, so let's look at this. So, in a quick explanation, bonding domains mean atoms, right? So atoms that have a bond with your central atom. Non-bonding domains mean lone pairs of electrons, okay? So let me show you the first example. I've got my central atom, and I have only 2 bonding domains. So it would look like this in order for the central atom to have a complete octet. So if you look at this shape, and you see it right here, this shape looks like a line, and so we call it linear. Okay, let's look at the next shape. If I have 3 bonding domains, meaning I have 3 atoms coming off of my central atom and no lone pairs of electrons, no non-bonding domains, what it would look like is this. Okay, notice no lone pairs of electrons, and I've got 1, 2, 3 bonding domains. 3 bonding domains, no non-bonding domains. This is what the shape looks like, and you can see it on the paper as well. Notice it is, as I manipulate it, it's all of your atoms are in the same plane, meaning if I had a piece of paper, it would all be on one piece. The piece of paper would cut straight through it. It would be all on one plane, one piece of paper. And so the shape of this is trigonal planar. Let's look at the next shape. All right, in this one I have 2 bonding domains, okay? And I have 1 non-bonding domain, meaning I have 1 lone pair of electrons. If you look at this shape now, notice that it looks bent. And guess what? That's exactly what this molecular geometry is called, bent. Okay, let's look at the next molecular geometry. 4 bonding domains, 1, 2, 3, 4. I've got 4 atoms attached, no lone pairs of electrons, no non-bonding domains. Okay, so if you look at this, okay, it looks exactly like this, and we call that tetrahedral. For the next one, 3 bonding, okay, so 1, 2, 3, and 1 non-bonding, or 1 lone pair of electrons. Okay, if you notice here, this looks a lot like trigonal planar did, except notice it's not all on one plane now. It kind of looks like a pyramid where you've got the purple atom on top, and then the bases are your 3 other atoms. And I therefore call this trigonal still, but it's trigonal pyramidal. And let's look at the last one. So I have 2 bonding, 1, 2, 2 non-bonding, or 2 lone pairs. Again, this shape looks a lot like what we saw up here, which was bent, and guess what? It is. This is a bent structure, okay? All right, so in these examples, I give you multiple examples. We're gonna go through the entire process that we've covered over the last 3 lessons. Counting valence electrons, determining the Lewis structure using the Vesper model, determining how many bonding and non-bonding electron domains a molecule has, determining its molecular shape or its molecular geometry, it's the same thing, and then also determining whether the molecule is polar or non-polar, which we looked at in the last lesson, okay? So let's look at the first example, Pi3, okay? So phosphorus has 5 valence electrons, iodine has 7, but there are 3 of them. So that's going to be a total of 26 valence electrons. I'm now going to draw out Pi3. I've got 3 iodines, okay, sharing electrons. My next step is to make sure everyone has an octet. So iodine right now has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Phosphorus here has 2, 4, 6, so I need to make that 8. Okay. Now let's look at the simulation to determine what the Vesper model shows this would look like. I've got 3 atoms. I've got 1 lone pair. And so this is what the molecule would look like. Okay, so what you just saw looks like this, to the best of my ability. So this is the Lewis structure based on the Vesper model, telling us that electrons are going to repel each other and atoms will take, and molecules will take whatever shape will minimize those repulsions. So I've completed step number 1, step number 2. Then it says determine the number of bonding and non-bonding domains. Okay, so for bonding domains, that means the number of atoms that are bound to phosphorus, my central atom. I have 1, 2, 3 bonding domains. And for non-bonding domains, which also means lone pairs of electrons, I've got 1 non-bonding domain. Okay. Then it says determine the molecular shape. So if I have 3 bonding, 1 non-bonding, you can either just look at this shape and tell what it is, or you can look at the 3 bonding, 1 non-bonding, but this is going to be trigonal pyramidal. And then finally, I'm asked, is this molecule going to be polar or nonpolar? Well, if I imagine I've got phosphorus here, and the iodines are pulling down, pulling down, pulling down. Nothing is counteracting that, pulling upwards, so that molecule would move, meaning the dipoles do not cancel. Therefore, this molecule would be polar. Okay, so there's one. Let's look at the next one. CH3Cl. Let's figure out my number of valence electrons first. Carbon has 4, hydrogen has 1, times 3, chlorine has 7. So that's going to be a total of 14 valence electrons. Okay? Carbon's going to be my central atom. I'm going to put the chlorine, it doesn't matter where it goes, I'm going to put it, just for the heck of it, over here now. Then I've got 3 hydrogens. Now I have to share electrons first. Next, I need to make sure everyone has an octet. So remember, hydrogens are the one weird exception, which are stable when they have 2 valence electrons. So all 3 of these hydrogens are content right now. Chlorine right now only has 2 valence electrons, so I need to add 6, 2, 4, 6, 8. And then carbon has 2, 4, 6, 8 already. Okay, let's quickly look at the simulation to determine what the Vesper model would look like. For CH3Cl, I've got 4 atoms attached. Keep in mind, one of these is going to be Cl and the other 3 are hydrogen. And it would look like this. Remember, it doesn't matter where your chlorine is. I'm going to put it down here. Okay. All right, so that is my Lewis structure based on my Vesper model. The next step that it asks for is determine the bonding and non-bonding. All right, so for bonding here, I have 4 atoms attached to my central atom, so I have 4 bonding. For non-bonding, I don't have any lone pairs of electrons, so I have 0 non-bonding. Okay. For the molecular shape, looking at this, you can either look at it and figure it out or go back to your table, but get used to being able to recognize the shape. This is going to be tetrahedral. An easy way to remember tetrahedral, remember tetra means 4, so the 4 bonding gives you tetrahedral. And then finally it asks if it's polar or nonpolar. So here's the tricky thing about it. Normally when you have a central atom and something's pulling up, an atom's pulling down, pulling down, pulling down that way, all of those would cancel out. The central atom would not move, therefore we would say that the molecule is nonpolar because the dipoles cancel. Here's the issue though. In order for that to be true, all of these atoms have to be the same atom, right? All of your outside atoms. So if all of these were hydrogens, you would be good to go. However, because you have a chlorine right here, that messes up the nonpolar statement. And therefore, because you have a different atom on the outside, this molecule is going to be polar because the dipoles do not cancel. Let's look at the next example. N2O. Let's figure out my valence electrons. Nitrogen has 5. I've got 2 of them. And 6 for oxygen, so that's going to be a total of 16. Let's draw this out. I'm going to have oxygen in the center because I only have 1 of them and I have 2 nitrogens. I'm going to share electrons, and I'm going to make everyone happy. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Let's count how many valence, and one thing I've been very sloppy with, and I apologize, I need to go back. I need to make sure I'm using the correct number of valence electrons for all of these. So let's check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm using the correct number of valence electrons. I apologize for not checking that before. For CH3Cl, 2, 4, 6, 8, 10, 12, 14. And I'm using the correct number of valence electrons. Sorry about that. Let's check this one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I am not using the correct number of valence electrons. So that tells me, because I'm using 20 right now, and I should only be using 16, I'm going to need a double bond. So I'm going to add 1 double bond here. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. I'm still using too many, which tells me I'm going to need to use another double bond, which means I'm going to get rid of those and get rid of those, so that nitrogen now has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. And oxygen has 2, 4, 6, 8. Now let's count my total number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, and I'm good to go. Let's quickly look at what this looks like with your Vesper model. Got 2 double bonds. That's what it looks like. And what you just saw is that it looks exactly like this. Okay? Now, bonding and non-bonding domains. How many bonding domains do I have? This counts as 1 bonding domain. This counts as 1 bonding domain. So I have 2 bonding domains. I have no lone pairs of electrons, so I have 0 non-bonding domains. And if you look, it is linear because it looks like a line. 2 bonding, 0 non-bonding is linear. Okay? If we're talking polarity now, nitrogen will pull towards it, oxygen, or the other nitrogen will pull towards it. Obviously, guys, this is a simplified version of determining polarity. To do it properly, we would have to actually compare electronegativities, but for simplicity's sake, let's imagine that's what's happening. Notice that they will cancel. If they cancel, that means that your molecule is nonpolar, and that is because your dipoles cancel. In that tug of war, that oxygen is not moving. Your dipoles cancel. Okay? Let's look at number 4. Okay, NO3 minus. Nitrogen has 5 valence electrons. Oxygen has 6 times 3. I have a -1 charge, which means I have 1 additional valence electron. So for total number of electrons here, I have 24. Okay, let's draw this out. So I've got nitrogen and 3 oxygens. Okay. Make sure everyone's happy. I'm going to add 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen needs to have 8, 2, 4, 6, 8. Let's count to make sure I'm using the correct number of valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm using too many, which tells me I need to add a double bond. Where I add that double bond doesn't matter. So if I add it here, okay, so let's now recount. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm using the correct number of valence electrons. A quick side note, okay, this is not how NO3 minus nitrate actually exists in the real world. This is actually a case of what's called resonance, where this double bond doesn't actually exist in one specific location. Instead, what it actually exists is an average of what it would look like if the double bond were here, here, and here. Now, the concept of resonance is beyond the scope for this class. You will sometimes see it drawn where you'll see a double arrow with a double bond here, and then another molecule with a double bond here. I'm not going to ask you guys to draw that. The fact that you're able to determine that this is the Lewis structure is sufficient for this class, and we're not going to get into concepts of resonance. If that interests you, I would love to discuss it with you further. I find it really interesting. However, for this class, this is all that I expect to see. Okay, so let's now determine what the Vesper model for this would look like. I've got 2 single bonds and a double bond. So what you guys just saw is that this is actually the correct shape using the Vesper model. So let's go on to talking about bonding and non-bonding domains. So for bonding domains, I have 1, 2, 3 bonding domains. Non-bonding domains, I have no lone pairs of electrons, so I have 0 non-bonding domains. Okay. If you look back at your table, either by looking at the shape itself or by looking at the 3 bonding, 0 non-bonding, you can see that the molecular geometry or the molecular shape is going to be trigonal planar. Okay. And then finally, polar versus non-polar. If you imagine a tug of war, oxygen is pulling nitrogen that way, and that way. Notice that nitrogen would not move. Therefore, because it doesn't move, that means the dipoles actually do cancel, which means that this molecule is going to be non-polar. Okay, let's look at the next and final example. Br2O. So let's first determine valence electrons. I have 7 valence electrons from bromine, but 2 bromines, and I have 6 valence electrons from oxygen, so that's a total of 20 valence electrons. I've got oxygen at my center because I've only got 1 oxygen, and then it's going to share electrons with bromine. Then I need to make sure everyone has an octet. So bromine right now has 2, so 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8 valence electrons. Okay, so right now I'm using 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I'm good to go. Let's quickly check with the Vesper model. 2 atoms attached, 2 lone pairs. So this is what it would look like then. So let's talk about number of bonding and non-bonding domains. Bonding, I have 2 atoms that are attached to my central atom, 2 bromine, so 2 bonding. For non-bonding domains, I've got 2 lone pairs of electrons, so 2 non-bonding. So if you look back, the shape is going to be bent. Okay, let's talk about now polar versus non-polar. Okay, if you imagine bromine pulling the electrons towards it, nothing is pulling up to counteract that, to balance it out. So oxygen would move in a tug of war, and therefore the dipoles do not cancel, making this molecule polar.